on the computer.
I just said it's working.
Working.
Is the live streaming okay now?
It's working, sir. Working, sir. Working. So I'm going to. Raja, sir, you ready? You be ready?
Yes, I'm ready.
Can you just give permission to share screen?
Yeah. Okay. Sure. Sure.
Nirmala madam is not here.
You can. Who is introducing?
Nirmala madam.
Oh. What happened?
Everything okay?
Yes, sir. Just 1 minute. Sir, I'm not able to share the screen.
Can you see?
Raja sir, the audio is too low.
My
Okay.
audio is too low.
Yes.
I'll speak nearer the computer because my volume is already, at least the volume of my speaker is already at, okay, I put 100%. That's the speaker. Can you hear me?
Yes, yes.
Yeah.
Okay. I'll try to speak a bit louder.
So I think that it's got resolved, right, George?
Yes, yes,
Yeah,
yes,
good.
yes.
Yeah, very good, very good. Nice. So I think we can get started.
Yeah, sure.
Yeah, and the participants, I think, are they coming in?
Yes, yes, yes.
Yeah. So I'll get started. Yeah. Yeah. So very good morning to one and all for the second day of the session. And today our first talk will be from Professor Dr. Andrew V. And it's my honor to introduce Dr. Andrew. Professor Dr. Andrew V is a professor at the National University of Singapore. He's also the director for Surface Science Laboratory in the Department of Physics at the NUS Faculty of Science. Professor V was awarded the President's Medal in 2008 by the Institute of Physics, Singapore, as well as a UK Singapore Partners in Science Collaboration Award in 2006 as a visiting scientist to Imperial College. V's research interests are surface and nanoscale science, scanning tunneling microscopy, synchrotron radiation studies of the molecule substrate interface, graphene, and related nanomaterials. He has published more than 400 internationally referred scientific papers. He is an associate editor of the journal ACS Nano since 2011 and serves or has served on several editorial boards. So thank you, Dr. Andrew, for accepting our invitation again. It's an honor to have you here. And I hand over the present session to you, Dr. V. Yeah.
Okay, thank you, Grace.
Thank you. Yeah.
I'll share my screen.
Yeah, you have to share your screen.
Can you see?
Yes, perfect.
Okay.
Yeah.
Okay. Thank you, Grace.
Yeah.
Thank you, the
Yeah,
organizers, for this kind invitation, and thank you all for tuning in so early in the morning. I believe it's 8 a.m. in India. It's a bit later in Singapore, and I guess most of you audience are in Asia because it's an unearthly hour in Europe and US. My talk today is on ferromagnetic 2D materials, and as mentioned, I have a surface science lab. And I'm also the associate editor for ACS Nano. So I hope you do read the journal and submit articles there too. And these are very interesting times. So NUS, there's a picture of NUS. NUS, like your university and many universities around the world. Okay. Okay, NUS is Singapore's flagship university. Our reputation is built on excellence of teaching and research and contributions to country and society. But as I was saying, like many universities in the world, NUS has turned to e-learning because of COVID-19. So I just wanted to share some data from some teaching data which might be of interest to you. So sometime around April, and Singapore went into lockdown. So we hadn't finished term yet. There was about 2 more weeks of term and the examinations. So everybody had to rush and turn their modules into e-modules. So it did appear a bit chaotic, but after all the dust has settled, the student feedback um, scores revealed something very surprising. In fact, in the scores for module effectiveness, and this is average of all the several thousand modules last semester relative to the same modules the year before, there was actually a very slight increase in the overall module effectiveness, which was very surprising. And although it's small because of the large number, it's statistically significant. Now, we were discussing what the reasons this were, because this is unexpected. If you turn into e-learning and e-exams at the last minute, you would expect students to complain, but these are just summarizes some of the positive keywords that they mentioned. In fact, many of them found e-learning very clear, very enjoyable, very flexible, and very comfortable. You see many of these words, and I think that's a good sign. It means that although this study is not very exhaustive and it only gave feedback of modules that turn e-learning halfway. But I think it bodes well for the future when we will see more e-learning in our classroom. And not only that, I think you will see a new normal of virtual conferences like this VCAN conference. I congratulate the organizers for a very excellent organization, and everything has been very smooth so far. I've enjoyed the talks. And certainly, such Zoom conferences, I've been to a few, they're very comfortable because the audience can be anonymous. They are comfortable. They don't have to dress well. They can sit in the comfort of their bedroom like I am in now. And perhaps you may have seen this message that succinctly illustrates what Zoom meetings are like. So in Zoom meetings, if you don't have your video on, you don't even have to comb your hair. So um, that's why I think the audiences tend to be larger. I hear there are hundreds of participants in this conference, which would be far more than if it was a physical conference in India. And I did invite my group members as well as former group members who are now in several countries all over the world, mainly China, but also in Australia and elsewhere. And I hope they are turning in and tuning in. And if you're tuning in, hello to all of you. And good to hear from you again. I hope you learn a bit more of what we're doing these days. So coming back to NUS, we have several research clusters. You can see where our university does have strengths in, and the one I want to focus on is material science because that concerns our work. And in the area of material science, there are several research centers that I'm involved in. The Singapore Synchrotron Light Source, we have a small second generation compact synchrotron light source, SSLS, on our campus. And one of the beam lines there, the surface interface nanostructure or science beam line or SINS beam line, was set up by our group about 20 years ago. It's very useful. And for this particular talk, we did a lot of XMCD magnetic dichroism studies here, as well as other spectroscopies. The other center that is very, maybe very well known, is our 2D center in NUS. It has a clean room, and students that need to make devices go to the clean room to make devices. But I must emphasize that my lab is essentially a surface science lab. So traditionally, we work in ultra-high vacuum. We work on surfaces and interfaces at the atomic scale. So our instruments in our lab look like all these vacuum systems. So we have two STMs. One of them, you can do non-contact AFMs. I'll just show a few STM images, but this talk basically is about all other work done. We also have MBE where we can do in situ MBE, and I will talk about MBE of magnetic 2D films. And we have SQL Lab for common usage. All the magnetic measurements in our lab were done collaboratively with other colleagues in Nusni and the 2D Center elsewhere. That's because we do not have any magnetic measurement systems in our lab. As I said, we are surface science lab. So today's work I'm going to present is a collaboration with many other colleagues on campus and overseas as well. This is my group, at least before COVID in December, having after lunch. As you can see, it's an international group. We have members, of course, from Singapore, from China, from India, from Indonesia, from UK. So you're most welcome to visit our group. So the scope of my talk today, I'm going to talk about 2D magnetic materials. I'll give a gentle introduction for those of you who are not familiar with this field. Then I'll mention 5 of our recent papers in the last 2 years. But of course, since I'm only limited to 45 minutes, I would just give a gist, an overview of what these papers are. And I'll talk about the future perspectives of this field, because this is a very new field, about 2 to 3 years old only within 2D materials. People didn't study magnetism until just a few years ago. So it's a very hot area, and some of you might be interested into getting into this area, especially if you have a background in 2D materials or magnetism. So how is this relevant to the conference? I believe your conference has a theme on flexible electronics. And of course, we see people talking about flexible electronics being devices of the future. They could be wearable, and of course, they're very thin and flexible. And 2D materials in particular are ideal for flexible devices because they are atomically thin. You could bend them, you could fabricate them on flexible substrates, and they can be bent and worn. And in particular, for 2D magnets, just like 3D magnets, they are useful in non-volatile storage, spin filters, spin injection, detection, and other 2D materials like graphene are very useful because graphene has very long spin diffusion lengths. It has a direct dispersion relation, so it's high mobility electrons, weak spin orbit coupling. And today we are going to focus on transition metal dichogonians. Nice. They're very interesting. They have strong spin orbit coupling. They obey Valley selection rules. They display the quantum spin Hall effect and so on. So we wrote a review last year in InfoMat entitled Van der Waals Magnets, Wonder Building Blocks for Two-Dimensional Spintronics. So this review was led by Chang Wen and Johnny with Rui's help. So we highlighted the synergy between the 2 existing fields of 2D materials and spintronics. And by bringing these 2 fields together, the future could really be promising for devices in 2D spintronics. So this is a summary chart that shows that in 2D spintronics, we utilize the charge and spin of your atoms in 2D materials. So you combine these 2 and you get 2D Van der Waals magnets. And these magnets could be magnetic, and they could be extrinsically magnetic, which means the magnetism is from defects or functionalization or dopant atoms, or they could be intrinsic, which means they are magnetic without any modification in its pristine form. So for example, chromium, germanium, telluride, iron, germanium, telluride, manganese, dichogonians, and so on. These have been shown to be magnetic. And of course, you can make a lot of Van der Waals devices from these materials. On the right, it shows that some of the challenges in this field is there's a need to be able to grow large area films in order to scale up your devices. And one technique which we will use and is particularly useful is MBE, because not only can you grow these films in very clean conditions, you can grow them controllably at the atomic layer thickness. and the tools you can use to characterize them. There are many of these magnetic tools, but they have to be sensitive to the monolayer level. So that's the challenge of this field. So other challenges and opportunities, we want these materials to be stable at room temperature, of course. We want them to have Curie temperatures as high as possible, if possible at room temperature, so that your material is ferromagnetic without the need for cooling. And of course, there are a whole loads of novel and exotic interface-induced magnetic phenomena, which people have studied at these interfaces and that have the potential for novel devices. So there's a very good review by Novoselov recently last year on 2D materials, which I shall use to illustrate some of the basic properties. So we know that in 3D systems, you can get a magnetic phase transition at a finite temperature, typically a Curie or new temperature. But in a 1D system, however, you can't get long range order. You can only get it at t equals 0. So it's difficult to make 1D systems magnetic. In 2D systems, however, it's at the border between these two extremes. So the existence of magnetic long-range order at any finite temperature depends crucially on the number of relevant spin components. This is called the spin dimensionality, determined by the physical parameters of the system. So let me explain what this spin dimensionality is. So this diagram from the review shows that at the top left, you have a spin dimension 1, you have an Ising spin system. So it's a 2D system where spins are up or down. As you can see, you have a finite Curie temperature and you can get this phase transition, and it's magnetic at low temperatures below Curie temperatures. And then you have this system where you have spins that can be in the plane. It's explained by the XY model, and the isotropic system where the spins can be anywhere. So to summarize, the Mermin-Wagner-Hohenberg theorem says that thermal fluctuations destroy long-range order in 2D systems at any finite temperature when the spin dimensionality is 3. That means in this isotropic system, it's a isotropic Heisenberg system. You can see there's no magnetism here, right? On the other hand, the 1D Ising system, you can get a phase transition at Tc, and Tc less than 0, it's magnetic. And in the planar 2D magnet system, in this case, spin dimensionality of 2, the XY model shows that there's no conventional transition to long-range order, although you get susceptibility diverging below a finite temperature. There's this Berezinski, Kotelitz, and Taulas have pointed out it's got to do with topological order. And in fact, these systems below a certain temperature, known as the Kotelitz-Taulas temperature, TKT, you have quasi-long-range order, which is a sort of magnetic order. So in 2D magnets, we can expect to see these topological effects that give some kind of long-range order. And in the data you see at the top right of different materials, you can see the Tc decreasing as the number of layers decreases. So let me first talk about, so this is the only equation I'm showing. So this shows the Heisenberg spin Hamiltonian. So for a magnetic system, so you can see that the first term, J, is the exchange coupling between nearest neighbor spins. So that is the common term we always see. But there are additional terms, A and gamma, and these are on-site, inter-site magnetic anisotropies. So these two terms relate to anisotropies, whereas the first term relates to the exchange coupling. With J is greater than 0, you get ferromagnetic materials, and less than 0, you get anti-ferromagnetic. So the key thing is that in the Ising or XY model, you can get a the case where A and lambda here is non-zero. So you have to take these two terms into account for those models. So I'm going to talk quite a bit on anisotropy in my next few slide in the papers that we do, because that we believe explains the origin of magnetism in many of these 2D systems. This is a review written last year by Xiang Chang's group, summarizing the 2D, the van der Waals magnets found so far. And as said just now, the Mermin magnet theory says that normally you can't get long range order because of thermal fluctuations. But if you include some anisotropy, you can open up what is known as a Magnon excitation gap, and you will lift restrictions imposed by this Mermin-Wagner module theorem. So you can see among the halides, recently there have been all these chromium halides that were observed to be ferromagnetic or anti-ferromagnetic in orange here. And in the chalcogenides, the more well-known FGC, CGC have been studied for several years, and they still remain magnetic in the 2D limit. So there's potentially a lot of materials. It's just that they haven't been discovered yet. Today, I'm going to talk about vanadium diselenide because I put it in dotteds because there's some controversy in this area. Okay. So I mentioned chromium iodide is people are excited over this material because bilayer chromium iodide is found to be anti-ferromagnetic, and as shown 2 years ago by Xiaotong Shi's group, it is possible to electrically control the 2D magnetism. So in this configuration where the chromium iodide is sandwiched between electrodes, you can see some kind of curve where you, at a zero field, there's these degenerate anti-ferromagnetic states, and higher or lower fields, high positive or negative fields, you can get flipping to ferromagnetic states. And they have shown also it's possible using the gate voltage to show a dependence of this flipping from ferromagnetic to anti-ferromagnetic states. And why is this important? This is important because if you want to make devices, you can't have large magnets around, but if you can use simple gate voltages to control the spin state, you can make storage or logic devices. Okay, coming to our results. First, I'm going to talk about vanadium diselenide, as I mentioned. Just as a background, I think you know from basic quantum mechanics, Pauli exclusion, Hund's rules, and so on. The 3D elements are interesting. From 3D1, 3D10, you get spin states and unpaired electrons in most of these cases. And the question we want to ask is whether transition metal dichalcogenides in the 2D limit are magnetic. So these are some of the compounds you would start looking for magnetism in. So the ones that have been studied so far, to our knowledge, is manganese and vanadium, right? They will be in a 4+ state because they are diselenides. So for vanadium 4+, you remove 4 electrons, you still have a single spin in the 3D state, and manganese, you have 3 spins. So you expect some spin. This is the paper 2 years ago from Kawakami's group on manganese diselenide, and they showed some magnetism in this monolayer. So this was one of the first studies showing magnetism in transition metal dichalcogenide. Another paper in that year in Nature Nanotechnology by the Betzel group in Florida also showed strong room temperature ferromagnetism in vanadium diselenide. And the reason why this excites a lot of people is because it's at room temperature and it's a strong ferromagnetism. Theoretically, it has been predicted that they have a strong magnetic moment although not as strong as in uh, some of these ferromagnets, like iron and cobalt. But the value they reported was an order of magnitude larger. So that raises certain suspicions. Why is it the magnetism was so strong? And this inconsistency did cast doubt on the use of bulk magnetic tools for measuring this ferromagnetism, because in this case, you're measuring everything from the substrate and any contaminants and so on. So, and this brings to mind the field of dilute magnetic semiconductors, where many people reported magnetic materials where this magnetism was caused by extrinsic contamination or defects. So the fact that they reported these exciting results, but several other people couldn't reproduce them. So this was a material that where there was a lot of interest in because of this controversy. And we were studying this material at the same time, and we couldn't find magnetism in that. So we eventually published this paper last year. The work was led by Johnny. So we use a whole range of techniques, including STM and so on. So as you can see from this figure, that's the spin, vanadium 4 plus as single spin in a 3D orbital, and that's the crystal field splitting because of the octahedral crystal field. The important result is the XMCD of the vanadium peak you see on the right, C. You can see that the dichroic signal, that means the difference between the absorption peaks in different helicities, so clockwise minus anti-clockwise helicities, which you can get on a synchrotron, gives a signal which is less than 0.2%. So it's barely above noise. So we don't observe any significant magnetism in this system. And these are the STM. We see charge density waves, so there's a certain periodicity. And STS shows that it's metallic, or at least there's a very small gap. So we have the metallic 1T phase, and it doesn't seem to be magnetic. So I must say the XMCD is important because you can get magnetic information at the element-specific level. So we did further magnetic studies, bulk magnetic studies, and you can see that squid shows no magnetic hysteresis, but linear behavior down to 2 Kelvin. And it's a positive slope in the outplane direction, indicating paramagnetic behavior, and negative slope in in-plane, indicating a diamagnetic response, which is probably due to the substrate background. And in the Z field and zero field cooling curves, because they're similar, it suggests there's the absence of long-range magnetic order down to 2 Kelvin and 7 Tesla. And the broad maximum in the susceptibility is characteristic of a low-dimensional magnetic system with short-range anti-ferromagnetic interaction. So, and the negative Weiss constant in the 1/chi curve indicates also supports the anti-ferromagnetic origin of the exchange interaction. But this magnetism is very small. And as illustrated in this diagram up here, you have these two spins which are anti-ferromagnetically coupled. But as you can see in this lattice arrangement, you have a frustrated spin in the center. It doesn't know whether to be up or down. So we postulated that vanadium diselenide is on the verge of being magnetic, but it's not magnetic. So that's spin frustration. Oh, this is further RPS measurements that shows van der Waals gap when cooling. Okay, so that gives evidence for the metallic state. Next, we studied this system, but by depositing cobalt on top of it, which is a ferromagnetic metal. We wanted to see whether we can make vanadium diselenide magnetic via an interface hybridization effect using cobalt ferromagnetic metal. So we use mainly XMCD because, again, as I said, this gives element-specific information on magnetism. And so we could this time see the hysteresis as shown in this table of contents figure. Just going through the results, we can see that long-range ferromagnetic order is obtained and is induced by direct contact with cobalt. And you can see the schematic, there seems to be anti-ferromagnetic coupling because in the XMCD, the peaks are in opposite direction. STM topography shows that you have a fully covered vanadium diselenide surface with some islands of cobalt. And there, of course, is the XMCD spectrum showing clearly that you have the cobalt hysteresis and vanadium hysteresis anti-ferromagnetically coupled in opposite directions. And there's a temperature dependence of this dichroism. So we have shown that we can make vanadium diselenide, a frustrated magnet, magnetic by putting a ferromagnetic material on it, right? So the next question we ask is, let's study other vanadium dichalcogenide compounds. So we studied vanadium ditelluride just to confirm that this material is not intrinsically magnetic. So here, this work is on metallic 1D, 3D1 electronic configuration. So this is very similar to the vanadium diselenide case. So we, again, did not see any XMCD signal. So it's non-magnetic. And again, all the properties are very similar. So we conclude a lack of ferromagnetism in vanadium ditelluride, which of course then supports our previous conclusion that the vanadium dichalcogenide compounds are not intrinsically magnetic. And in fact, our work is supported by the Betzel group, the same group that showed that vanadium diselenide was magnetic at room temperature. They also did vanadium ditelluride, and in this case, they didn't observe magnetism. So the XMCD signal, you can see there's no dichroism. So in fact, we think then that the first conclusion may not have been correct. So this shows that the various vanadium dichalcogenides are non-magnetic. But we can use vanadium as a dopant in other non-magnetic 2D materials like molybdenum telluride. And in Betzel's group, they showed in another paper that they could make this material magnetic, okay? However, there's another controversial result last year from our colleagues group, Lo Tianping, who's in chemistry department. And it turns out that he was working also on the same material, but by exfoliation, by electrochemical exfoliation. So it's a chemistry method. And they showed that by chemically exfoliating this material, it is magnetic. But we must remember that this kind of exfoliation method is very dirty and there could be contaminants on it. And they did further studies to study the magnetism of this material if they saturated it's full of defects. If they saturated the defects, so sorry, they did some calculations. So this shows that if the defect concentration increased, it becomes more magnetic. But if they saturate it with thiols or oxygen, it becomes less magnetic. So it suggests that defects have got something to do with the magnetism. So building on this, we continued this study on defects to understand why some people measure magnetism in vanadium diselenide. So this work just came out this year, done by Rebecca, who is a final year PhD student, and all these collaborators. So essentially, she was studying the defects and its role in magnetism in monolayer vanadium diselenide grown by MBE, right? So there's no other extrinsic contaminants. So this is what under STM the surface looks like. So if after depositing you see some of these triangular defects, but they're not so many. But if you anneal it, the density of these triangular defects increases as illustrated here. And if we zoom in on this line defects, we can build a structure of this selenium deficient defects. It turns out that these line defects have a structure as shown here, which requires a displacement of half a lattice constant of the adjacent row. Okay, so it forms 8 member rings as seen in these STM images. So that's the line defects, and you can increase the line defects on this vanadium diselenide monolayer by just by simply annealing. And these are the magnetic measurements. So the XMCD on top shows that there's no magnetic signal when it's pristine, but it shows that the defective vanadium diselenide shows a weak but discernible magnetic signal, dichroism signal, right? And the bottom, the MFM images, on top is the pristine, and the bottom is the with defects, and I think this on the right is the phase spectra, and the percentage, you can see some difference in images, but if we look at the statistics of the percentages of at different phases, you can see a shift. So clearly, the more defected vanadium diselenide shows a phase shift, so it shows magnetism. Okay, so we have magnetic measurements on this material to show that magnetism indeed, and these are the DFT calculations that show indeed that we have this structure on the right with the 8 member rings. You can actually get an increase in the magnetism per atom. So we conclude in this paper, and we hope we have resolved the controversy that selenium deficient defects are responsible for lifting the frustrated magnetism previously reported in monolayer vanadium diselenide. So that's an interesting model, and that hopefully gives some insight into these 2D TMD magnetism. So to summarize, our current understanding of vanadium diselenide magnetism is that we have grown everything by MBE, which guarantees the highest level of cleanliness. And ferromagnetism, the Betzel group reported some evidence of ferromagnetism, but these were not reproducible by others. And our colleague did a chemical exfoliation method, but the results suggest it could be related to vacancies, selenium vacancies. And the fact that many people and us, and including the Betzel group, also didn't show magnetism in vanadium diseleride also suggests that this material is intrinsically not ferromagnetic. But although it is not ferromagnetic, we showed that by depositing a ferromagnetic metal like cobalt, we could induce interface hybridization and make it magnetic. So we conclude that it's on the verge of magnetism, and the role of defects, right, could induce uniaxial magnetic anisotropy. As I mentioned before, anisotropy is very important because it opens a magnon gap. It lifts restrictions imposed by the Mermin-Wagner theorem, and hence you can make a 2D material magnetic. Now I'm coming to the end. How much time do I have left?
Yeah, how much? Okay, you can proceed another 5 minutes.
Okay, yeah,
Yeah.
I started 10 minutes late, so I'll do 5 minutes.
Yeah,
I'll
sure.
just briefly indicate, show our latest work and then some future perspectives. So this work has just been published in Nano Letters. This work was done by a PhD student, Chu Rui, with Zhang Wen, and basically it's on the exchange bias effect of van der Waals heterostructures now. So now we are taking the antiferromagnet chromium trichloride on a ferromagnetic material, FGT, and studying exchange bias. And exchange bias is basically the physical phenomena where the spins of a ferromagnetic magnet are pinned by those of an antiferromagnetic magnet. And this phenomena is very important in data storage. All the data storage devices you use depend on this exchange bias. And I think, okay, the interesting thing is, okay, we are not working in the extreme monolayer limit, I must say, but they are very thin films. As you can see, let me skip the details, but if you can see, you have the optimal level of this exchange energy at about 20 nanometers chromium trichloride on 30 nanometers FGT. So these are very thin films, not in a monolayer limit, in a few layer limit, because it's difficult to make these materials monolayer. But nevertheless, you see this exchange bias, and exchange bias basically breaks the symmetry of this hysteresis. You see this red arrow, you have a shift of the hysteresis to one side, that's the exchange bias. Just moving back to the previous one, if you work on just FGT, it's symmetric. You don't see this exchange bias. So only when you put this antiferromagnetic CrCl3 at the right thickness, you can see this exchange bias. So without going to details, this is a pictorial explanation of this exchange bias effect. It shows the pinning of the spins in this bottom case where it can't quite flip, the ferromagnet can't quite flip, and that results in the shifting of the hysteresis loop. So to summarize, we have managed to fabricate a simple antiferromagnetic and ferromagnetic heterointerface device that shows this exchange bias coupling. It's about 50 millitesla. So it's at low temperature, 2.5 K. But nevertheless, it's a step in the direction of using these 2D heterostructures for real devices. So that's our latest work. And of course, in a review, there's a review this year that talked on various other works that have used this effect and other related effects in a whole range of devices, from spin filters to tunnel barriers, spin top transistors, and spin valves, and so on. So this will be a hot area in the coming years. Now, my future perspectives, my last couple of minutes, now you know that we are going through an interesting revolution in what is sometimes known as the second quantum revolution, whereby your technology is, whereas previously it was based on many particle quantum systems, nowadays people are interested in manipulating single particles, single quantum particles, single qubits. And you can see the claim of Google of quantum supremacy last year. So 2D materials and magnetic materials in particular are very useful for quantum information science. In this review by Hersam's group last year, here shows quantum graphene quantum dots acting as qubits, so they can be coupled. And here shows 2D boron nitride becoming single photon sources needed for such quantum devices. And these sources are basically defect states. We are interested in using, because our other work in the group is on molecular self-assembly. So we are interested in molecular spintronics as an alternative to using 2D materials. And I wouldn't go through this, except to say that people have observed magnetism in, for example, copper tylosinane. This was a Nature paper in 2013. And our recent work shows that you can self-assemble such tylosinanes. This is cobalt tylosinane, or HOPG, done by Zhang Lei and published, just published as well. So it shows that there is potential for using such molecules for quantum application. So finally, I'd like to acknowledge all the group members, especially those in red who did the work presented today: Rebecca, Chure, Zhang Lei, Johnny, Wen, and Yuli. And of course, there were external collaborators as well in IMRI, as well as the Southeast University and ALS, Diamond. We had to do a lot of magnetic measurements on synchrotrons overseas as well. Lin Min Chong, NTU 20, and financial support from all our funding agencies. So thank you for your attention. And my last slide is just an advertisement of a book that we published just last year on semiconducting 2D materials and devices that may be of interest to those students who are working in this field. Thank you very much.
Thank you, Dr. Andrew, for such a inspiration and wonderful talk. So we have many questions from the participants, and I'll pick few questions in want of time. So the first question is, do these single-layer magnetic materials show reorientation transition either with thickness or temperature?
Yes. So the answer is yes, but we didn't do this study. This study was done, I showed briefly the Xiaotong Shi's group on chromium triiodide. At the monolayer, it is ferromagnetic. In the bilayer, is anti-ferromagnetic, and so on. So there is a thickness dependence of the magnetism in some of these materials. So it's very interesting class of materials.
Yeah. So the second question is, are bulk magnetic measurement techniques used for these few layers 2D materials, and what about the MFM studies?
Yeah, we did use some bulk magnetism studies, like the Nature Nanotechnology paper. They use bulk studies. We did use, you saw some squid measurements and so on, but there is a danger because you are measuring everything, the substrate and contaminants and so on. And you also have a sensitivity issue because you're measuring just one monolayer. So the techniques we like best are XMCD, which is X-ray, this dichroic magnetism, which is the synchrotron dichroic technique, because it can measure the magnetism with element specificity as well as surface sensitivity. So that's a monolayer. MFM, as you saw in our work, could detect the magnetism in the phase mode. We could see the magnetic signal, although it was very subtle in our phase images. So I would say XMCD is probably the best technique. You can use other belt measurements, but just be careful of contaminants and substrate effects and so on.
Yeah, thank you, Andrew. One other question from Dr. Sahu. How the magnetism and exchange interaction can be controlled based on various layers in vanadium selenide, VSE2?
Oh, we haven't done any experiments controlling the exchange interactions in vanadium Se2 yet. We did the first study on the chromium chloride FGT system, and where under at low temperatures and high magnetic fields, we can show some exchange bias. And the Shi Xiaotong's group showed electrostatic control via the gate voltage of the magnetism in bilayer chromium triiodide. So there's still a lot of work to do in this area. No one has work. We have there's still a lot more work needed on the vanadium systems. So yeah, keep a lookout.
Yeah, yes. Yeah, thank you. So last question. Magnetic measurement of 2D is very challenging due to weak signal and strong substrate effect. What protocol is required to measure it?
Yeah. So as mentioned previously, you are right. The signal is very weak and cleanliness is very important. Hence, you saw in all our studies, we did MBE growth. So MBE, you can grow very clean films. And if you have MBE system attached to your characterization system, then you can do in situ measurements. So you can transfer them without exposing to air, or else you can cap the film and then transfer it. So you'd be careful of contaminations. And of course, in most measurements, you need preferably a surface sensitive measurements. So spectroscopies, soft X-rays, as mentioned, XMCD and so on, are very useful because they probe only its top few layers. So I would say if you follow these protocols using the right techniques and the right cleanliness control, you should be able to do measurement.
Yeah. So thank you, Dr. Andrew. Though there are lot of questions, I had to ask only few in want of time. So thank you once again, for such an interesting talk, and thank you once again for accepting our invitation to come over here
Thank
and
you very
grace the
much.
occasion. Yeah, our
Thank you.
pleasure. Thank you. Yeah.
Thank you.
Bye, Dr. Andrew.
Bye-bye.
Bye.
Hi, Didi.
Hey, Andrew. Nice to
Long
see
time no
you.
see.
You've got a wonderful background.
Oh, yeah.